Alright, I'm going to create a pthreads directory in our class code, and we'll go ahead and go clear. We'll go ahead and start working on one, so let's go pthreads.c. Include, well, you're going to use pthreads, you probably should include pthread.h, just going to throw that out there. Include stdio.h, int main, int argc, char star argv. Open this back up, return 0. Alright, so what are the commands you want to learn? Well, first big one is pthread create. Create a thread. Alright, include pthread. You create a pointer to a thread container. Any attributes you want to send to it. This is for stuff like you want the thread to have its own certain space, or maybe clear all of its device drivers for this, or devices, sorry, for the thread. There's different attributes you can send to the thread of what type of thread you want to create. You need a void star start routine void pointer. This is a function pointer to, well, a function that takes a void star as an argument. And then you can send it void star, aka the arguments afterwards. So this is the basic idea of how you would create a thread. So let me go in here. Let me actually create this variable at top. Int num. Ooh, that's bad. Threads equal. Let me make it 4 for now. So then we'll have pthread underscore t thread sub num threads. All right. So that's our number of threads. 4. Int I equals 0, I is less than num threads plus plus pthread create. That's where you have threads plus I, no attributes. We need to come up with a function, so we'll do void star function, void star args. Go ahead and put this guy at the end. We'll have it print out. Isn't that amazing? So function, and we'll have no arguments for now. No one wants to have an argument. So for int, oh, I'm sorry. So once we create it, the next thing you want to know about is pthread join. Join with a terminated thread, aka once the thread is done, it basically waits until the thread is done. That's all this does. Pass the thread, and if you want to store the return value into a variable, you can. That's that void. Notice that that function returns a void star. It would pass it in right here for you, so you could actually dereference it and work with it if you wanted to. But we're not going to mess with it for now. I'll just copy and paste this. Join. It takes the actual thread itself, and we don't care about the return value. All right. Now let's compile and link with -pthread. Let's see if I can do this correctly. gcc -pthread pthread.c -o pthread. Ooh. No. We'll do a little bit more on this code. For example, if I turn this up to 4D, recompile, and then run it right afterwards. Hey, high 40 times. All right, that's a little bit much. Let's go with 10. There we go.
Make it 400.
Ooh, that should break. It didn't break.
But they had to run 400 destroyed faster than they were being created.
Possibly. There could have been many things that were causing this. Maybe Linux upped its count from 256 to something else. You know what? There, 9,000. It's over 9,000. Nope, still good. All right, let's go back to 10 or 11. I like 11. Okay. Notice how fast that was. I think if we did 4, it could be a little slower. But anyways. Any questions on this code so far? All right, if you want to pass arguments to a thread, I am recording, right? Okay, good. Phew. Oh, that would have been bad. This is how I recommend doing it. Type def struct. We'll call it thread arg type. We'll just have int ID for now. All right, and then when I'm down here, I'll do thread arg type args and the number of threads. And now if we want to pass something to this function, we'll just do, where are we? Args plus I, arg sub I dot ID equals I. All right. And here I can go, hi, I'm thread number %d. Args ID. So, making a whole list of thread args to each thread. I packaged them in a struct, so if I want to add something to it, I can pretty easily. Pass it to the function here. I can grab it back here and print out my ID. Go ahead and save it. Run. Oops.
Where are you passing it?
Oh, hold on. I'm passing it right here. There's a quick type def that I messed up on. That's okay. I'm going to give this a quick underscore because then I'm going to do thread arg type pointer args equals, because I need to cast it. Because right now it's a void pointer. It needs to be cast to the actual struct so it knows what it is. There we go. 14036257891.
They're bad at
We're bad at counting. Hey, that's impressive that it did it the same way twice in a row. It didn't?
It was 1-4 the first
Oh,
time. then
now it's 1-2.
0, now
Yeah,
1-2.
so this should be expected a lot with threads. They're going to be executed all over the place.
But 10 was always last.
10 was always last. Any questions yet? Comments?
So we created a thread. Called the arguments. I keep going back to the argument. The args plus 1, where'd you define ID thread arg? Oh, okay. Number 30.
The ID for arg. Do you want an example to show performance improvement here? It'll take me probably 5-10 minutes.
Seems like you want to do that, so let's go.
I don't know. It's up to y'all. It's typing. It's up to y'all. You don't know? Okay, we'll do it. Long sums. I'll just call it star sums. Sums equals new. Whoops. We don't use new in C++. No, that's good. Size of long times, what we got, num threads?
You should use cout though.
Cout?
So it's 0 initialized.
Oh, I see. Calc? Yeah. That could happen. Sums sub I equals 0. I can do it there. Let me change this to sum so it makes more sense. Alright. How do I want to do this? Num threads. Let's first knock that down to 1. Let me make sure I've coded this all correctly. Nope! Oh, because malloc hasn't been included. That's cute. There we go. Hi, I'm thread 0. Perfect. And let's go define some length. I don't know. Define len. 20. Sure. For int I equals 0, I is less than len. We'll do this right. Whoa, that's not what I want. Oh, we need to know how many threads there are. We'll make that global. I love making things global. There we go. So we need to know what the start is. So int start equals, so it's my I. Who was it going to be? First we need to know the count. So the diff, call it diff. Len divided by num threads. That's how much work each block of threads is going to do over a summation. Is it fuzzy down there?
Yeah.
Wow. But it's clear up here.
Yeah. It might be better if you turn the light off.
Or it might just be the projector.
I think it's a projector. It looks pretty fuzzy. That helps.
It's probably just a little out of
It's
focus
top
at the bottom.
focused.
Yeah, it's
Yeah, the focus is up, yeah, higher.
There we go. All right. Thread. I'll just say, and then we'll have int start equals, let's see, args-id times diff, and then yeah, we'll just do that. Going from %d to %d. So start comma start plus diff. Now, assuming I type this correctly, which may or may not be the case.
You've got start is equal to arguments, ID.
So that's where it's going to start, I++ up to the diff, and then we'll have some sub, so args-id plus I. Perfect. Looks like we're going to need a bigger number. Looks like we're going to need oh, that's not bad. How long did that take? Oh, 2 seconds. All right. What if I increase that to 2 threads? I'm totally not making sure I'm doing this correctly. Hey, 1.4 seconds. Well, that's cool. And the user time was 2.9. That's beautiful. So the real time was 1.4 seconds. So it only took 1.4 seconds going to 2 threads. What do you expect it to happen if I bump it up to 4? This is a hard question.
So the time to go down.
Okay, expect time to go down. By how much?
Less than half.
Yeah.
Less than half. Close to half or not close to half?
I would say close to half.
Close to half. All right, let's do it. Not much. Why is that the case? No one asked me what processor I have on this machine. It's only a dual core. It's actually a dual core with hyperthreading, which is why it looks like I have 4 cores, but I really only have 2. I have only 2 real cores and 4 fake cores because if you recall from simultaneous multi-threading, it's able to interleave it. So there's some extra performance I can get by running more cores or more threads, but not by too much. 1.2 seconds from 1.4. So if I put this to 40, what do you think is going to happen?
Time's gonna go up.
Wow, it went down? I would have expected it to go up. Huh. All right, 400.
Doing more work. though.
Intel magic.
Yeah, this is Intel magic. All right, we're going to get rid of that print statement because I think that's what's causing some of this. 1.03. I pretty much hit my low, haven't I? I don't think I can add any more threads here. This should definitely slow down. Well, there we go. Finally coming back up. All right. Yeah, it's Intel magic. Looks like the kernel was able to thread things or interleave threads pretty efficiently with the memory system is my guess of what's going on here. When they were starting to get some cache misses and whatnot, it was able to move it together, but there's not much memory going on
So it was just what, summing
from 0 to n.
and from n to n plus n.
It from 1 to whatever, and then it would chop it up in blocks to the number of threads, and then each thread would do its block and store its result in an array. Now the master thread, which I haven't did yet, should sum the final array back together and then give you the result, but I haven't done that yet.
Because, I mean, we were getting bigger numbers each time,
For this?
weren't we?
No.
For the user. Or
So with one thread. Oh, let me go ahead and put my print statement. Notice it's going from 0 to 1, blah, 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 right? If I were to move that up to 4, still
The
still
last
do.
thread was still going to the same number.
Yeah, I mean, and if you recall, they're going to be out of order now. So, you know, thread 4 is going here, thread 39 is doing that. But, you know, they're different orders here, but it's still, it should still be the same.
Well, thread 4 is going from that number to above that number.
Mm-hmm. 35 is definitely higher. Notice how many digits are in each one? So the same number of digits. That looks fine. Yeah, that's fine. I mean, it looks fine to me.
Okay, yeah, never mind.
Okay. But knows that there was definitely a wall. What I'm actually impressed here is it took a long time before that number started going up. That really does drive home that a lightweight process is really lightweight nowadays. It's doing very little in your operating system. So creating extra threads does not cost much. If I were to write the same program with processes, it would be far fewer processes would start slowing this thing down because you got to set up shared memory and everything else. Any questions on this one? Great.